So can anybody see something in the screen? Would you say yes if you can see something? Sorry about this. So give me 5 more minutes. Sorry about this. Okay, now it works. Yeah, give me 2 minutes. I think it's working now. Okay, so sorry about this. And okay. Okay, sorry about the delay. What happened is that I changed my main machine. I thought everything will work fine, but looks like there are some security settings I had to change, which I didn't know just 5 minutes ago. So, okay, so that's why I mean, my tablet didn't really work, but now it's working fine. Okay. So, yeah. So can everybody hear me? Would you say yes? Okay, so thank you very much. And we are now moving on to the next topic. So the next topic is the program's specification and their proofs. So chapter 3. By the way, if you have any problems of hearing my voice or seeing what's really going on the screen, anytime you can raise your hand or you can just write down something in the chat box. Okay. So this is a new chapter we're gonna study. And then the chapter is about program verification. So this is motivation. Just a bit. So when we write programs, often we want to, first we want to write down what the program is supposed to be, often. So think about the following program. The program, what it does is, let me just write down code first, and then maybe I will ask you to figure out what's really going on. So it's a program which assigns 0 to A, and then to X, while B is greater than or equal to 3, to the following. And then the first thing is that we decrease A by 3, and then we increase A by 1. Okay, so this is a program. Maybe I will give you 10 seconds to think about what this program is doing. You don't need to answer it, but just think about it a little bit. So what this program does is that it takes X as an input, and it produces some output which are stored in two variables, B and A. And what it does is that it computes integer division. So for instance, if X has a value 4, integer division by 3. If you divide 4 by 3, and then in its quotient, in Korean is called mok. Its quotient is 1. In Korean, mok is 1. And then remainder in Korean is called namoji. So the remainder is going to be happen to be 1 as well. And for if you do the same thing for 5, the quotient is going to be 1, remainder is going to be 2. So what this program does is that it computes this integer division and stores quotient in the variable A and stores the remainder in the variable B. Okay, so that's what this program is doing. So I will call this entire program as C div3 because it computes the integer division by 3. So now suppose we wrote this program and we know that this program is correct. Looks like it's correct, but we want to formally state its correctness, its property. And then also want to say that, want to prove actually these programs satisfy their property. So sometimes we want to formally specify and the behavior, the intended behavior of this program. Instead of just saying, this is computing integer division by 3. I mean, we want to formally say exactly the same expression such a way that some machines can check what we said is actually correct or not. So we want to formally specify its intended behavior. And the second thing we want to do is that we want to have some formal way to check this specification is correct. We want to formally prove that the program indeed satisfies the specification. So the first step is essentially writing formally what we want. Second step is we want to check formally that the program indeed satisfies what we want. Okay, so these are the two things that we want to do. But without anything else, we can't really do this. Okay. Also, these two things are pretty important, very important. That's because they form the basis for automated verification tools, which take program like the one that you see on the screen and then produces proofs. Sometimes some automated tool even discover the appropriate likely specification for this program and then come up with a proof for that specification. So these are the kind of tools that actually you can find in practice, and some companies are using such a tool. So then the question becomes, what are the bases? I mean, how we can do number one and number two? And what we're gonna study is this number one and number two using something called while logic. That while logic has two key components. I mean, the first component plays a lot smaller role. The second component is more important. The first component allows us to specify, do the number one. Second component allows us to do the number two. So before actually talking about the while logic, if I write down the formal specification of the first program, it can be written like this. So we say, look, we write something like this. So what this program, what I wrote means is that the first one is called precondition. And then what you see in the middle is a program that we want to think about. The last one is called postcondition. In the textbook, the precondition is sometimes called precedent, and then the last one is called consequent. But typical, more common terminology is precondition and postcondition. And what I wrote means is that it's a specification, so it expresses what we want for this program, and that specification says if x is greater than or equal to 0, okay, when we start the program, if x is greater than 0, and then program terminates without any problem, then the final state satisfies what's written as a postcondition, and the postcondition say x is equal to 3 times a plus b, and then b is greater than 0 but smaller than 3. What I wrote in the postcondition is exactly saying a is the quotient of dividing x by 3, and b is a remainder. Okay, it's a formal way to specify what I just wrote about, what I explained to you before. Okay. So this is the kind of things that we want to do, and the second, we will also learn that how to write the proof for this specification. So in the textbook, it actually talk about, let me write one more. Textbook, it talk about two versions of while logic. One is for the partial correctness. And then the other is for the total correctness. we will talk a little bit about the total correctness specification, but we will focus mostly on the partial correctness part. Total correctness is more difficult, but I will just tell you what the concept is, but our main focus will be on the partial correctness. Okay. So now where should we start? The starting point of understanding core logic, or sometimes it's called axiomatic semantics, is to understand what I just wrote over there, the specification mechanism. Okay. So the core logic and pretty much any other formalization about programming languages always go through the process that we discussed so far, which is define the syntax and then define the semantics. That will clarify what's really going on, or formally explains what's really going on. Once you write down the syntax for appropriate concept that appears in the things that we are talking about and write down semantics, then we can carry out some further studies, like we come up with some proof principles and so on. So here we're gonna first think about something called specification. And then first thing we're gonna think about the specification is a syntax. So specification is a new, you can say non-terminal in our grammar for our language, or it's a new syntactic category. Then this syntactic category is defined very simple way. We are thinking about, there are only two cases. The first case is for partial correctness. The second case is for total correctness. The first case looks like this. It has an assert inside the curly parenthesis, and then we have a command. And then we have another assert for the post condition that I told you. So that's a one case. And this is for the partial correctness. And then the other one is for the total correctness that looks very similar, but instead of using curly parenthesis, we are using square parenthesis. Assert. There's a command. And there's another assert. Okay. So what does it tell us? So typically the instance of this first guy, second guy is written like this. We have a assertion P, command C, another assertion Q, or assertion P, command C, and then assertion Q. And then the first one is called for the partial correctness, and then second one is for the total correctness. The first one is sometimes called triples. Then second, or sometimes it's called a triple. So, the second one is usually called total correctness triple. And here's the important bit I want you to know about. This is that what does it mean? Okay, we are studying mostly for the first guy, but I want you to know the difference between these two, informally as well as formally. Okay. So what does it mean? So in both cases, the P appears in the first parenthesis, talking about what should some properties on the preconditions, properties on the states before running the command C. Okay. And then Q are talking about the properties of states after running C. So that's why P appears before C and Q appears after C. But there are just some, so P is talk about initial states, Q talk about the final state of the command. But they are a little bit different. The first one say, if P is true initially, And then C terminates. So then Q true at the final state. So that's an informal description. Okay, that's what we talked about before. And we talk about this divide by 3 example. And the second one is actually a bit different. It says that if P is true initially, so P is true in an initial state, maybe just instead of writing initial state. So if that's the case, then Command C terminates when it runs at that particular initial state and the final state satisfies Q. So you can see some difference. The one difference is that the termination part, in the first case, it's an assumption. So if the program doesn't terminate, we don't care about in the partial correctness. And then the termination part in the second case is a conclusion. So this statement is stronger. It says that if the precondition is true, then Command C always terminates. Okay. So, okay, so you can see that the total correctness is a stronger conditions than the partial correctness. So you might wonder why one should care about partial correctness, because often we want that if something is true, some legitimate precondition is true, we want that our program to terminate under that condition. Okay, but it turns out dealing with this total correctness is more difficult and requires a bit more work. And often just focusing on the partial correctness gives a nice proof principles, as well as still proving this partial correctness, really help us to find all sorts of bugs in a program. Okay, so that's the syntax. Now let's just try to make this intended meaning of this partial correctness triple and the total correctness triple more formal by semantics. Then how to do this? So we want to give a semantics, which is using, as usual, we give this map. In this case, that map takes specification. And then it will produce the only one Boolean value, because either specification is true or false. And then the Boolean value is B, which is either true or false. So what I will do is that I will write down the intended meaning for partial correctness, and then I will give you 1 minute so that you can write down the semantics for the total correctness. So often it's written in the textbook, it's written spec, but I'm gonna omit this most of the time. Okay, now what's the meaning of partial correctness? The partial correctness is like this. It's a PCQ. We have to say when it is true, so it's true. Otherwise, it's false. When the following condition holds, okay, if and only if the following condition is true. The conditions say that for all states sigma, if precondition is true under this state, so state sigma is the initial state, and program terminates, it's not equal to bottom. So then the post condition has to be true under the final state, at the final state. So this is exactly the formalization of the informal meaning that I explained to you. So here's an exercise. Define the meaning for the total correctness. So that's one exercise I want you to do. And there are two other exercises. I mean, the one more exercise is that, so check which one of the following is true. Okay. So here I'm gonna write down something very weird, but that will help you to see some corner cases of, also see the difference between this partial and total correctness triple. So we have false while true do skip. So this means the program goes to the infinite loops. False. True. Program is the same and the post condition is the same. And then another one is for the false. False. And then the last one is false and true. True and false. And then which one? So if it's true, this is called valid. And which ones are valid? So that's the second exercise. So I will give you 2 minutes. Yeah, 2 minutes to think about, solve both of them. Okay, so let me give you an answer here. So the first case, the answer is that it's very similar to the interpretations, the semantics for the partial correctness, but instead of putting this termination part in as an assumption, so we put it as a conclusion, which means that it now becomes a requirement for every state, every initial state, precondition is true. So then our program should terminate, should not be equal to bottom. And then post condition should be true in at the final state. So that's how the answer for the first. And as I said, the termination part moved from the assumptions to the conclusions. That means that there's total correctness indicates what usually say some stronger property than what correspond. I mean, always say stronger property than corresponding partial correctness triple. Now for the second problem, you see that if the precondition is false, okay, then this assumption part in both cases, here as well as here, the assumption part will never be true, okay, because I mean no state will satisfy assertion false. So in both cases, they are going to be valid. Now the question becomes, what's about the second and the fourth? For the second one, if the precondition is always true, because it's always satisfied because it's precondition just true, then my program diverge, it go into the infinite loop all the time. So in this case, maybe use this one. This case, I mean, this condition, the program, if program terminates, that condition will not be satisfied at all. Okay, so the second triple is also valid. That's for some silly reason, which is the program always diverges, so we don't have to worry about this final state. Now the last one is not valid because this termination part is no longer in the assumptions, it's in the requirement, it's in the conclusion. So the total correctness, if it's true, the program always terminates and then satisfies the false, and the program doesn't really terminate at all, so it's not valid. And in fact, I mean, this is for this exercise, if you write down C, any command C, if the post condition in the partial correctness, if the post condition is false, precondition is P, this means the C does not terminate. When the precondition P holds. Okay, it's because otherwise, I mean, the false is a post condition which we will never be able to satisfy. So this is a bit weird way to specify divergence or non-termination of a program. Okay, so then, I mean, just like I showed you before, we can, another more meaningful example is, I mean, for the divide by 3 program, it was like x is greater than 0, C divide by 3, and then the post condition was x is equal to 3 times a plus b, and b, value of b was between 0 and 3. Another more meaningful example is, suppose we have a Fibonacci number. So if x is greater than 0, or greater than 1, actually, n is greater than 1, we can write down program that compute the Fibonacci number of n and store in a variable in a variable x. So then we can say what the program does is that it computes Fibonacci number of n. Of course, when you write a specification, there should be a way to express Fibonacci number. So this is defined using mathematical notation. Okay, so, and then in fact, in both of these cases, replacing this partial correctness by total correctness doesn't really change. It's also specification, stronger specification because we talk about termination. But in both cases, it's also true because both programs have a it behaves well and it terminates under the reasonable precondition. But if it goes out of the reasonable preconditions, for instance, n becomes negative or x becomes negative, then sometimes partial correctness is true, sometimes, but most of the cases of total correctness condition is going to be false. Now there's a specification part, but then another, as I said, the other big part of this whole logic is about proofers. So which is, so I said there are two questions that we want to consider. One is how to formally specify intended behavior of a program. The answer in whole logic is to use partial correctness triple or total correctness triple. Okay. And then the second part is that now we are given such a specification as a part. From now on we'll focus entirely on partial correctness. We are given such a partial correctness triple. So then the question becomes, how can we prove this given partial correctness triple? And then, so while logic comes with a bunch of so-called proof rules that allows us to do this partial correctness proofs. Proves these partial correctness triples. So the proof rules have the form of the inference rules that I briefly mentioned when we talk about this language for assertions. So predicate logic. And so these proof rules, they have this kind of form, which is it have a specific some fact premises v1, v2, and vn, and then it has a conclusion v. Typically, these v's are partial correctness triple quadruples like p, c, q. In the case that we are talking about, conclusion is always going to be a partial correctness triple like p prime, maybe some other command d and q prime. Sometimes one of these premise is going to be about validity of some assertion. So we have a write down some assertion p, but this means that this p is true always. In other words, p is valid. So, and then informally what this specification tells us, I mean, this inference rule tells us is that if v1, v2, vn, they are all valid, then conclusion should be valid. So that's what this this type of inference rule is telling us. And there are two types of inference rules in while logic. One are closely tied to the programming constructs. And it's so while logic prefers, there are two groups. So the first tied to the programming construct, and the second is not tied. I mean, so then the second kind of rules, sometimes called the structural rules. And the first, I mean, the silly name is non-structural rules. So what do I mean by the tied to the program construct? I mean, we have a program construct called sequential assignments, and then sequential compositions, and so on. So we have skip, assignment, sequential composition, if then else, and the while loop. Each of these constructs come with a proofer. Okay? So we have one proofer for each of these constructs. Actually, not necessarily one, but proofer tied to each of these constructs. So these are the proofers that fall into the first group. And the second group is not really tied to this. It can be applied to any command. So that's why it doesn't make any assumptions about the form of the command. So that's why it's called a structural rules. And okay, I think the best way to see it is to actually see some actual rules. So let me start with the non-structural rules. First, I will first write down the three non-structural proofers. The first is that we have a proofer for skip. So we want to prove quadruple for skip. So what should we do? And the rule said, if we just put the same pre and post condition, we can have a proof. Why this is the case? That if the P is true initially, then skip doesn't do anything, it terminates with itself. So then P has to be true finally as well, right? Because skip doesn't do anything. And a bit more non-trivial rule is called, so this non-trivial rule is called rule for assignments. So we have an assignment. Now, suppose we want to prove post condition Q is true after the assignment. So what should we do? And then the assignment rule say, actually, what you need to do is prove version of a Q where X is replaced by E. So if you prove that the Q with X replaced by E is true initially, after the assignment, Q will be true finally. So a bit weird, but it's if you use it, you will see that that's actually what makes sense, and I will tell you why that's the why this rule is correct. And then the third rule is called the rule of sequential composition. So suppose we want to prove that the sequential composition satisfy P precondition, P C1 C2 Q. What should we do? And then the rules say that to do so, to prove this, you need to prove C1 satisfy some, satisfy what, triple with the same precondition P, but with some post condition R, and then show that on the R, C2 Q is also true. Okay. So if you do so, then the rules say that this quadruple, that the conclusion is going to be true. And then there are two more rules. Okay, maybe just writing down all the rules and then do some practice that may be more useful. Now we have another, the rule for if then else. If then else say, I want to prove P C2 Q. So if I want to prove some PCQ where my command C is an if then else statement, what should we do? And it say that do case analysis. Okay, it say consider P, consider the case where B is true, and consider the case where P is false. And then on the true case, only consider the command in true branch and establish post condition, intended post condition Q. And if the P is false, and consider only command in the false branch and prove that intended post condition is true. So that's for the if then else. And while the last bit is the while loop. This is actually the most difficult part, usually when you do the proof. Now in this loop proof rule for while, we have to use the so-called invariant. Okay, I will first write down the rule and explain what does that tell us. The reasoning about while is not very easy because we have no idea how many times this while loop will be unrolled during the execution. So in such a case, so we have something which can be repeatedly applied. The typical way to reason about this in computer science, as well as in mathematics, is to think about invariant, which is some fact which is true whenever this command C start to execute in any iterations. So that's what this I, which is an assertion, called invariant, is doing. So we say that to prove something about the while loop, the proofers say we have to find invariant I. And then that invariant has to be true when we run this while loop in the beginning. So that's what this, we can only reason about the case when invariant is true in the beginning. And then I has to be an invariant, which means that the body of the command has to preserve the invariance. But because body will always run under the condition B, so we only run the body of the loop when we enter the loop, so the loop condition B. So C has to establish the invariant I under the assumption about pre-states, which is the invariant I is true, and Boolean B is true. The loop condition is also true. So under that conditions, if C establishes I, that means that, so if the I is true in the initial state, the body of C preserved the invariant I. You can kind of see that the invariant will be true when the loop terminates. So that's what the word is telling us. I will be true when the loop terminates. And then because the loop terminates, the Boolean condition, the negation of the loop condition is going to be true. Okay. So now for pure proof, from the perspective of doing the proof, what this rule tells us is that to prove something about the while, we first identify the loop invariance. So this is, I think the maybe better way is called loop invariance. We have to identify loop invariance. And then we have to show that's actually a loop invariant, which means that the body, so that's what this premise is telling us. If we can show the body C preserve I under the loop conditions, so then we can conclude what you see in this rule, which is if I is true initially before running the while loops, then I will be true after when the loop finishes, and also the negation of the loop condition will be true there. So this is the other rules. Then let me just write down the last bit, which is the rule for consequence, structural rule. So there's many structural rules, but there's one rule that we will look at, which is the rule of consequence. The rules say, if we prove some PCQ, then we can strengthen the precondition. So if P prime always implies P, and Q always implies Q prime, so this means P prime implies P is true for all states. Q implies Q prime is true for all states. So then we can replace P by P prime, replace Q by Q prime. So that's what the rule is telling us. And I mean, if you think about this, it looks like we are losing some information. So we are strengthening the precondition, weakening the postcondition. So this is losing information, but it turns out this is extremely useful when you do the proof. And actually, without it, we can't really prove many things. So here, I think the best way to do this, get used to this, is to do some exercise. So let me give you an exercise. Okay, so here's an exercise I want you to do. Using all these rules, prove the following. Prove so this is the part of divide by 3 program. Is greater than or equal to 0. So prove this, and also prove times A is B. Is greater than 0. So prove both of these triples using the proof rules that you see on the screen. So I will give you 4 minutes to do so. Okay, so I will show you. There are many ways of doing the proof. And so it's a bit like we are giving some basic tools. How to use these tools well is an art. Okay, so that's why there's a big research programs on automated program verification. Because I mean, there are many ways of automate these kind of ideas. But I will show you one particular way of doing this proof, which has some flavor of running program backward. Okay, so let me do that. I think the proof will be essentially the same, has a very similar pattern in both cases. So I will deal with this second case, which is a bit more difficult. So how to do this? So we start with our conclusion, which is x 3a plus b, and then b greater than 0, and b greater than or equal to 3. And we have a command, b becomes b minus 3, a becomes a plus 1, and then x 3a plus b, b greater than 0. Okay, now we'll watch which rule to apply. We apply, in a sense, the idea of this particular way of using for logic proof rule is to run program backward with respect to the post condition. So sometimes this is called a predicate transformer semantics, but you don't have to worry about this, but the intuition is we run program backward. So how to do this? So we have a post condition here. And then the first command, so we're gonna run program backward. And then what justifies us to run program backward is the rule for sequencing. So this rule for sequencing, say if you have a sequential composition of two commands, you can first take care of C2 and then take care of C1. But intuitively what's gonna happen is that when you take care of C2, because we start with the post condition Q, we're gonna, in a sense, run program backward, the C2 backward to obtain R. And then once we get R, we run C1 to obtain something P. Okay. And then finally, this P that we obtain may be different from the precondition that we are given here. Then we're gonna match them together by using the structural. So run program backward, finally we fix mismatch by using structural rule. So that's what's gonna happen. So if you run program backward, so first we take care of the second command. So I'll just write it like this. We have the same post condition and we have an assignment. So we now use the rule action for the assignment. The action for the assignment to say, the rule for the assignment to say that take the post condition, replace any updated variable by expression. So here updated variable is a. So we can, if we replace it by a plus 1, and that's going to be an instance of this assignment rule. So if you do so, we get x becomes 3 a plus 1 plus b, and b is greater than or equal to 0. And that's it. I mean, because this is a rule which doesn't require any premise at all. So we, in a sense, have a proof of this. So here, what happened is that this a is replaced by a plus 1. Then now the rule for sequencing says start with what we obtained, the precondition that we obtained in the last command, which is this guy. X is equal to 3, a plus 1 is b, and b is greater than or equal to 0. And then we look at the other assignment. It becomes b minus 3. And the precondition is also fixed. This is what we have to show. Now the question is how to prove this. And we do something similar. We run this assignment program backward again. So that's going to give us the post condition remains the same. And if you run the assignment backward, so then what we have to do, this case is we just have to replace B. Here B appears twice. We have to replace B by B minus 3. So if you do so, then the result is going to be x equal to 3a plus 1 plus b minus 3 and b minus 3 greater than or equal to 0. But this is also the completed proof because the rule for assignment doesn't require any assumption at all. So we apply the rule for assignment twice to move post condition backward. First the second command, next the first command. Now, what we have to do, we have to, but still there is some mismatch. Okay, the precondition that we computed here, that's not exactly the precondition that we started with. Okay, so they are a bit different, and the fixing this match is done by this structural rule. So we have to, in this case, show the following implication is always true, which is if x is 3a plus b and b is greater than or equal to 0 and b is greater than or equal to 3, is it always going to imply x is 3a plus 1 plus b minus 3 and b minus 3 is greater than or equal to 0? And the answer is yes. If you look at the right-hand side here, I mean, if you expand it out based on the algebra things, the basic algebra that you learned, so 3a plus 3 plus b minus 3, so it's exactly the same as 3a plus b, and then b minus 3 is greater than 0 is implied by b is greater than or equal to 3. So this implication is true. Formally, if you do everything in the computer automatically proves this using axioms and some well-established proof mechanisms. But here we are doing some informal reasoning when it becomes, well, we just use the semantics when it, in this implication check in the while logic. So if you do so, we can see that this implication is true. So this is a completed proof of the, of the this command, the second exercise. And first exercise can be done exactly the same way. We take the post condition here. So we take post condition here and we move it backward using the second command that will give you some intermediate assertion that we have to deal with. And then we do the apply the assignment action again to move it with respect to the first command. And then there is a mismatch between, what we obtain is not exactly the precondition that we are given, but we use these structural rules to show that the given precondition implies what we computed by, this backward execution. Okay. So, right. Okay. And then this proof rule for if then else. So if you just push this idea of backward execution, actually, you can do it with you can do it in the absence of the while loop. And for if then else rules, it has to be modified a little bit. So I think the right rule is going to be, so the rule has to be, looks like this. It's exactly have the same power as the rule that's written here. But here's a rule which is more suitable for backward execution. So we run C1 backward with respect to post condition Q, obtain P1. Run C2 backward with respect to Q so that we obtain P2. Then we combine them together. And here we have if P C1, C2. And the condition is C, I think it's B, and so it's a B implies P1, and negation of P implies P2. Okay, so that's how you can combine them together. So, I mean, the rule that I just wrote is a bit less conventional than the rule that I wrote in the beginning. They have, I mean, if you have one rule, you can derive the other rule and vice versa. So these rules have exactly the same power, but the rule that I just wrote is more suitable. I mean, it's more in line with this backward execution idea. We have if-then else statements, we have a post condition Q, and then we run C1 backward, C2 backward, and combine the result together. Right. But as I said, this is a particular way of using the proof rule that I wrote there. Okay. And there are another way to use proof rule forward, which is, but in that case, instead of using this assignment rules, we are using some other assignment rule, which is based on so-called strongest post condition assignment rule. Yeah, so that's, I mean, that one, once you use this, in the absence of a while, I mean, you can also read all these proof rules as a forward execution. So why I'm saying all of these. So one point I want to say, besides, I mean, about this logic, is that, I mean, this logic allows us to prove properties about program. But there's another very important aspect about this logic, what this logic actually teaches us. So if you think about the programs, then the only way, I mean, the kind of very common way to think about the execution of the program is to run program forward, right? Just given an input, you run program, you get an output. But once you lift your view on the program as state transformation, given state, it produces an output state. You view it as assertion transformation. In other words, assertion corresponds to set of states. So if you lift it to the assertion transformation, or on the level of these logics, so then you can have a much more flexibility. You can view program as running forward with respect to assertion, also running backward with respect to assertion. So you can have a much more flexible executions of program with respect to assertion, and they form the basis of the different automated verification tools adopt a different perspective about this. Also in program analysis, there's something called forward analysis, backward analysis. They are possible because we are not working on the single state. We are working on assertions, which essentially means a set of state. So core logic, it's a logic for proving properties, but it is also useful for generalizing the view of the execution. Now, once you have these two, okay, so let me finish with the proof of this. Once we have these two, then actually we can complete the proof of the divide by 3 program by using this while loop rules, and then again sequential composition. Okay, how can we do this? So for the divide by 3 program, so we have a C divide by 3. I mean, that has two parts, which is has an initialization part. That's exactly what I wrote there. So this part is the same as the part written here. Then it has a while loop. B is greater than 3 to B minus 3, and A becomes A plus 1. So then the specification was if X is greater than or equal to 0. And then the post condition was that we want X to be 3A plus B, and B is between 0 and 3 without including 3. Okay. So, but then let's just write down post condition a bit without abbreviation at all. So just say p is smaller than 3. And actually, to make it really formal, write it like this. It's not the case that p is it's not the case that p is smaller than greater than equal to 3. Okay, so now how can we complete the proof? And then we use what we proved for the solution using the solution of the exercise. We can make some of the following plan. Okay, because we have because we have a sequential composition of 2 commands, we have to pick some intermediate assertion here. And furthermore, because this is a while loops, we want these intermediate assertions. You can choose any intermediate assertions and then do you use rule of consequence. But because it's a while loop, we want intermediate assertions to be around this invariant. Okay, and what's going to be an appropriate part of the invariance? We know that if we use the rule for the while loops, okay, let me just go a bit up. Yeah, if you look at the rule for the while loops, then the conclusion is invariant and negation of the loop conditions. So if you look at this, but the conclusion here, we have a negation of the loop condition, and then the remaining part is this guy. So we may say, okay, the loop invariant, if loop invariant is of this form, 3a plus b, then that intermediate assertion is true after the first command. Then we are done. Okay, so and also we show that this is indeed a loop invariant. But we already proved, and let's just use green, prove that x greater than 0, and then this initialization part, this post condition is true, 3a plus b and 0 greater than b. So that was our first exercise that we solved over there. And then for the other part, which is, so here we have to use 3a plus b and 0b and so on, and while, and this here. But for the while loops, to do the reasoning for the while loops, we have to use the loop invariance, and the loop invariant proof requires that we put the candidate invariance and then loop condition, which is b is greater than equal to 3. And then we have to say body of the loops, and we establish this invariance. And that is exactly what we did on here. So by putting all these things together, we can complete the proof of this divide by 3. And sorry about overrunning time and also all the mess in the beginning of this lecture. Let me just give you an exercise and then finish. So we finish off this part. We spend about like 20 to 30 minutes in the next lecture to finish off this part and move on to the next chapter. And some exercise I wanted to think about is that first is a proof for assignment, where we have a P assignment. Then we want to put appropriate things on the conclusion, this post condition part for arbitrary P and assignment. So what this should be. So that's the first exercise. The second exercise is more of the proof exercise. So if you try to prove programs like, write down what triple for Fibonacci number computations, and then also Euclidean algorithm that you learn in algorithm course, and write specs. and formal proofs of Fibonacci number program and Euclid algorithm. And both programs, you can find it in the lecture notes. So actually in the lecture notes, you can also find the specifications. So try to prove correctness of those programs. Okay, so that's it for today, and sorry about all the mess. Okay, so thank you very much, and then I hope all of you have a nice vacation.